6 minutes ago, one claim began racing across screens. Scientists had detected a real wormhole. Yet evidence inside supplied research points toward something stranger, because space-time tunnels remain theoretical, while researchers have already built laboratory-based magnetic versions under controlled conditions. So what triggered sudden shock? And could today's mystery become tomorrow's doorway between stars? Before we trace Einstein's hidden shortcut, comment your choice below, yes or no. Subscribe for discoveries that challenge everything familiar. Zero homework, just instinct. Keep watching. Since the distinction separating an odd signal from history's first confirmed cosmic passage comes down to clues most headlines leave out. Headlines leave out the reason wormholes were taken seriously long before anyone could claim to detect one. The story doesn't begin with a strange signal, a telescope, or some hidden object in deep space. It begins with Albert Einstein. In 1915, Einstein presented the field equations behind General Relativity. Don't worry, we're not about to turn this into a math class. The basic idea is much easier to picture. Matter and energy can bend space and time. Imagine a stretched sheet with a heavy ball sitting in the middle. The surface dips around that weight. Stars and planets affect space-time in a similar way, and stronger gravity means a deeper curve. Then something unexpected happened. Einstein hadn't fully solved every case hidden inside those equations. In 1916, Carl Schwarzschild found an exact solution for a simple, round mass. That work helped reveal a strange possibility. Gravity could become so intense that space-time would curve into what we now connect with black holes. For decades, black holes sounded almost unreal. Yet the math came first, and observation followed much later. That history matters because wormholes also emerged from Einstein's equations. In 1935, Einstein and Nathan Rosen described what became known as the Einstein-Rosen Bridge. Picture two dots on a sheet of paper, A and B. Normally, the shortest path is a straight line across the page. Now fold that paper until both dots nearly touch. Suddenly, a tiny passage through the folded sheet could connect places that once seemed far apart. That's the simple idea behind a wormhole. A shortcut joining distant points through curved space-time. Think about what that could mean. Andromeda sits about 5 million light-years from Earth. Even light needs roughly 5 million years to cross that distance. But if space-time itself could fold in the right way, the normal route might not be the only route. Sounds like science fiction, except the idea came from real physics. Here's where the excitement needs a break. A mathematical solution isn't the same thing as an object found in nature. Equations can allow something without proving the universe actually made it. Wormholes still sit on that uncertain side of the line in the material we're examining. Black holes once lived there too. Theory pointed toward them long before direct observational evidence became strong enough to change how people saw the idea. That doesn't prove wormholes will follow the same path. It only explains why scientists don't throw the concept away. And now our mystery gets harder. If some new signal really came from a wormhole, the name alone wouldn't prove anything. Researchers would need signs that ordinary stars, black holes, or other known objects couldn't easily explain, because from our three-dimensional view, that entrance wouldn't necessarily resemble the glowing tunnel movies taught us to expect. Its shape, light, and warped background could look far stranger at first. So before anyone calls this a cosmic shortcut, there's one question we have to answer. What would a real wormhole actually look like? Probably nothing like the flat tunnel you've seen in diagrams. Those pictures are useful because they turn a hard idea into something our brains can handle. You see a sheet representing space-time, 2 distant points, then a curved bridge connecting them. Simple. But we don't live on a flat sheet. We move through 3 dimensions, which means a wormhole opening would have to be pictured differently. From our view, it could look more like a sphere. Imagine floating toward a strange ball in space. Instead of seeing a solid surface, you might see another region through it. Light around the opening could appear bent. Stars could look stretched, shifted, or wrapped around the edge. Move closer, and the whole scene might change with your position. Turn around, and Earth could seem to shrink behind you while the view ahead bends into a circular world. That's why the wormhole shown in Interstellar looks so different from the usual funnel drawing. The movie presents it as a sphere, because that gives us a better way to picture how a higher dimensional shortcut might appear from ordinary space. If this is already bending your brain, subscribe, because separating real physics from movie images is exactly where these stories get interesting. Now comes the harder part. Seeing something round, bright, or badly warped in space wouldn't prove we had found a wormhole. The universe already contains objects with gravity strong enough to bend light. A strange image can be exciting without being a new doorway through space-time. So what would scientists need? They'd need evidence that refuses to fit the normal explanation. Think of it like finding footprints outside your house. One mark means very little. Several matching prints create a pattern. Add a camera recording, a clear path, and details that rule out ordinary causes, and your case becomes much stronger. Wormhole evidence would need that same kind of buildup. This matters because, according to the material we're following, nobody has yet seen a space-time wormhole. The idea comes from theory. Scientists have created models, proposed possibilities, and tried to imagine what one could look like, but practical confirmation remains missing. That makes any sudden detection claim far more serious than a flashy picture. A real candidate would have to survive questions designed to destroy it. Could a black hole explain the signal? Could normal gravitational lensing create the strange light? Could another known object produce the same pattern? If the answer keeps being yes, the wormhole claim gets weaker. But suppose those ordinary answers begin failing. Suppose the distortion behaves in a way researchers didn't expect. Suppose the object seems to reveal geometry that a normal black hole can't easily copy. Then the story changes, because scientists wouldn't just be asking what they saw, they'd be asking whether spacetime itself had opened a path somewhere else in the universe today. And that's exactly where excitement can become dangerous, because seeing something strange isn't the same as proving what caused it. Remember what happened with black holes. The math pointed toward their existence long before humans could actually observe strong evidence for them. Wormholes haven't crossed that same line yet. According to the material we're following, nobody has directly seen a spacetime wormhole. Scientists don't even know whether nature creates them. That means any claim detection faces a brutal test. First, researchers have to ask whether something we already understand could explain what they're seeing. A black hole has extreme gravity. It can bend the space around it and affect light coming from objects behind it. So an image that looks twisted, stretched, or almost impossible isn't enough. The strange part has to survive every normal answer. That sounds frustrating, but it's how discoveries become real. Imagine seeing a door standing alone in an empty field. Finding the door is strange. Finding it open is stranger, yet neither proves there's another world behind it. You'd have to walk around, inspect every side, check what's holding it up, then find out whether anything truly passes through. A wormhole claim needs that same level of care. Here's the detail that changes everything. Even if scientists found an object matching a theoretical wormhole picture, that still wouldn't automatically make it a usable shortcut. The equations describe possibilities in curved spacetime. They don't promise a safe tunnel waiting for a spacecraft. That difference is huge. One question asks, can wormholes exist? Another asks, can anything cross one? Those sound almost identical. They aren't. The original Einstein-Rosen Bridge came from the same broad world of relativity that gave physics black holes, but turning that mathematical bridge into something you could enter creates another problem. Gravity strong enough to twist space-time, that much isn't gentle. You aren't talking about driving through a tunnel between two cities. You're dealing with conditions tied to some of the most extreme objects imaginable. Now picture the claim from the beginning again. A strange signal appears. Researchers notice something unusual. The internet sees the word wormhole, and suddenly people imagine ships crossing millions of light years in seconds. Science has to move slower. Possible isn't detected. Detected isn't confirmed. Confirmed wouldn't mean traversable. That latter matters because each step demands evidence the one before it didn't have. Skip even one, and an exciting mystery can turn into a false conclusion. But suppose, just for a moment, that every test worked. Imagine known objects failed to explain the evidence. Picture researchers becoming convinced that the geometry really did point toward a wormhole. Humanity would face a much darker question, because finding the entrance would only solve half the mystery. You'd still need somewhere to come out. And according to the theory in our story, the thing waiting at that other end may have to behave like the exact opposite of a black hole. That sounds strange until you see the problem. A wormhole needs an opening. According to the material we're following, Einstein and Nathan Rosen connected that idea with the huge gravitational pull around black holes. Gravity there becomes so strong that space-time bends in ways ordinary places never allow. That gives us something powerful enough, at least in theory, to create the kind of tunnel we've been talking about. But getting inside isn't enough. You need to get back out. Imagine entering a tunnel whose far end is another black hole. Everything near that exit would still be pulled inward. Instead of crossing space and emerging somewhere new, you could become trapped inside the very shortcut meant to save you millions of years. Suddenly, the greatest highway ever imagined starts looking like a cage. So theorists face an odd question. What could sit at the other end? The answer suggested in our source is something with the opposite behavior. An object that doesn't pull everything inside, but instead allows things to come outward. That object has a name, a white hole. Before we go there, notice how much the story has changed. We started with a claim about detecting a wormhole. Then we learned that finding strange geometry wouldn't prove one exists. After that came another problem. Even confirmation wouldn't mean humans could travel through it. Now we've reached an exit that may require something nobody has confirmed either. That's the trap hidden inside the dream. Every answer creates another question. A black hole is famous for its point of no return. Once something crosses its event horizon, getting back out isn't an option in the usual picture. Light itself can't escape. That's why these objects appear black. A white hole flips that idea. Instead of having a boundary you can enter but never leave, the source describes a white hole as having a boundary nothing from outside can cross. Matter could come out, light could escape, yet nothing would be allowed back inside. Russian physicist and cosmologist Igor Novikov used the term white hole in 1964, according to our material. Scientists have explored the idea as a time-reversed version of a black hole. Think about that for a second. One cosmic object swallows, the other spits things out. Put those ideas on opposite ends of a theoretical bridge, and you can see why the picture becomes tempting. Something enters through one side, crosses the connection, then emerges through the other. There's just one massive problem. Nobody knows how nature would make that second object. We have ideas for how black holes form. Massive stars can collapse, leaving behind regions with crushing gravity. But what process would run that story backward and create a white hole? That question has kept the idea in the world of theory, and it gets worse. Some arguments suggest white holes may clash with a basic rule governing how disorder changes in nature. Others have tried to connect them with the birth or death of extreme cosmic objects. So the exit we need may be harder to explain than the entrance itself. Yet one strange flash in 2006 would give this mystery another turn. On June 14th, NASA's Swift Observatory detected a powerful burst of gamma rays from deep space. Astronomers gave the event a simple name, GRB 0064. What happened next made it difficult to forget. Gamma ray bursts are among the most energetic explosions we can observe across the universe. In the picture presented by our source, scientists expected an event like this to come with signs of a massive star meeting a violent end. They searched for that familiar clue. It wasn't there. Something had exploded with stunning force, yet researchers couldn't find the stellar evidence they expected. That missing piece opened the door to a much stranger idea. Could this have been a white hole? Notice the word could. GRB 60614 wasn't confirmed as one. The source says a white hole explanation was proposed because the event seemed unusual. But a strange event isn't automatic proof of an exotic object. That lesson should sound familiar by now. Unknown doesn't mean wormhole. Unexplained doesn't mean white hole. Mystery isn't confirmation. Still, think about why the idea attracted attention. A white hole is supposed to behave like the reverse of a black hole. Nothing enters from outside, while matter and energy can emerge. If something like that appeared in space, a sudden burst might sound like the kind of clue worth investigating. For a moment, the pieces seem to fit. Then physics pushes back. There's a basic idea called entropy. You don't need a textbook to understand it. Tear a sheet of paper into tiny pieces, and making those scraps return perfectly to their original state is far harder than tearing them apart. Nature tends to move that way. Black holes fit this picture more easily in the source's explanation because they swallow matter and leave us with a growing puzzle about what happens to everything that fell inside. A white hole seems to ask for something closer to the reverse process. That creates trouble. Some scientists have argued that such an object may conflict with the second law of thermodynamics. Others have explored ways white holes might still appear under extreme conditions. One possibility goes all the way back to the beginning of everything. The source describes an idea that the Big Bang itself could be compared with an enormous white hole with matter rushing outward during the birth of the universe. Another possibility begins with death. Stephen Hawking argued that black holes aren't eternal. Over immense periods, they can lose energy through radiation and eventually disappear. That raises a haunting question. What happens to the information connected with everything that entered them? Some ideas suggest a white hole-like state could play a role. None of that gives us confirmation. Instead, it gives us two cosmic objects tied together by unanswered questions. A black hole that can swallow and a theoretical white hole that could release. But here's where our story takes a turn nobody needs to imagine. Scientists have already created something they actually called a wormhole. It happened in a laboratory. And unlike the cosmic version we've been chasing, this one was real. In 2015, scientists created what they called a magnetic wormhole inside a laboratory. That name sounds like the breakthrough we've been waiting for. But there's an important catch. This device didn't bend space-time, open a doorway to another galaxy, or send matter across millions of light years. It worked with a magnetic field. Normally, a magnet has two poles, north and south. Break that magnet in half, and you don't get one north piece plus one south piece. Each new piece still has both poles. They stay linked as part of the same magnetic structure. Researchers found a clever way to make that connection appear very different. Using special materials, they built a device where a magnetic field could enter at one end and emerge from another, while the field between those points was hidden from outside detection. From the perspective of the magnetic field, it looked as though the path had crossed an invisible gap. And that's why researchers used the word wormhole. Not because a spaceship could enter it, not because time had been broken. The comparison came from how the magnetic field moved. According to our source, the setup used a high-temperature superconducting material called yttrium barium copper oxide, kept in a liquid nitrogen bath. The device separated the apparent magnetic poles in a way that made the field seem to disappear at one location and return somewhere else. Stop there for a second. For almost this entire story, we've been dealing with equations, possible objects, and cosmic ideas nobody has directly confirmed. Now we finally have an experiment carrying the wormhole name, yet it also shows why that word can mislead people. A magnetic wormhole isn't an Einstein-Rosen Bridge. It doesn't prove that a tunnel through space-time exists somewhere above our heads. It doesn't turn the claim from our opening into a confirmed cosmic discovery. What it does prove, within the experiment described by our source, is that scientists can engineer a system that makes a magnetic field behave in a wormhole-like way. That's smaller than interstellar travel. It's also real science. And sometimes the smaller breakthrough matters, because it forces us to ask a better question. What if the dream of crossing impossible distances doesn't require finding a natural tunnel at all? Think back to our folded sheet of paper. Every wormhole idea so far has depended on finding a shortcut between distant points. But there's another theoretical approach. Instead of opening a tunnel from here to somewhere else, what if you could change the space around a spacecraft itself? That possibility has a name. It was proposed in 1994 by theoretical physicist Miguel Alcubierre. His idea doesn't ask a ship to race through normal space faster than light. Instead, the space ahead would contract, while the space behind would expand. And if that sounds even stranger than a wormhole, it should. Because now the shortcut isn't a tunnel. The shortcut is space itself moving. That's the heart of an idea called the Alcubierre drive. In 1994, theoretical physicist Miguel Alcubierre proposed a solution built around a strange possibility. Maybe a spacecraft wouldn't need to fly through space faster than light at all. Maybe space could do the moving. Picture a ship sitting inside a bubble. In front of that bubble, space-time contracts. Behind it, space-time expands. The ship stays inside while the region carrying it shifts forward. Think of standing still on a moving walkway. You aren't sprinting across the floor. The surface beneath you is helping carry you forward. Alcubierre's idea takes that simple picture and pushes it into the world of curved space-time. That distinction matters. Einstein's relativity tells us that moving through local space faster than light creates a serious problem. But the idea described in our source tries another route. Instead of forcing the spacecraft itself to break that limit, the geometry around it changes. Sounds perfect. It isn't. The material we're following presents the Alcubierre drive as a theoretical solution, not a machine scientists have built. No engine is sitting inside a secret hangar waiting for someone to press a button. There's no crew preparing to ride a warp bubble toward another galaxy. We have an idea. That brings us back to the same lesson wormholes taught us. Math can open a door before nature does. Black holes began as strange results connected with equations. Wormholes also appeared inside that mathematical world. White holes remain theoretical. A magnetic wormhole was created in a lab, but it didn't transport people or bend space-time into an interstellar tunnel. Now the Alcubierre drive gives us another possible route on paper. Each step sounds closer. None gives us a starship. So why should any of this matter? Because the real story isn't that scientists already know how to cross the universe. It's that physics keeps producing ideas where distance behaves differently from the way everyday life teaches us. A table looks solid, space looks empty, distance feels fixed. Yet relativity tells us space-time can curve. Massive objects can bend it. The universe isn't simply a giant rigid box where every route must remain exactly as it appears. That leaves a question bigger than any headline. If nature allows space-time to bend, stretch, and curve, could there be a way to control those changes someday? Our source doesn't answer that. Nobody in the material proves an Alcubierre spacecraft can be built, just as nobody there proves a traversable cosmic wormhole has been found. But now notice where we've arrived. We started with a supposed wormhole detection. We ended up facing something even stranger. Perhaps humanity's first shortcut between stars won't be a tunnel waiting for us to discover. Maybe it will be something we have to create. That possibility is why these equations still matter more than any viral claim. And before we decide whether that dream belongs to science or fiction, one final distinction changes everything. Possible isn't proven. That may sound like a small difference after everything we've explored, but it separates one of humanity's greatest potential discoveries from a story we simply want to believe. Go back to the beginning. A claim appears saying a real wormhole has been detected. Within minutes, those words can race around the world. People picture a glowing doorway floating in deep space. Some imagine another galaxy waiting on the other side. Others jump straight to time travel. Yet the material we followed tells a different story. Wormholes remain theoretical. Einstein's equations gave physics a way to describe strange curves in spacetime. Einstein and Nathan Rosen developed the bridge that later became tied to the wormhole idea. That gave scientists mathematics worth studying. It didn't give them a photograph. White holes pushed the mystery further. If a theoretical tunnel needs an exit behaving differently from a black hole, an object that allows things outward sounds tempting, but white holes haven't been confirmed in the material either. Then came GRB 0606114. That strange event raised questions, and a white hole explanation was suggested. Still, an unusual explosion wasn't enough to turn possibility into proof. After that, we reached something real. Scientists created a magnetic wormhole in a laboratory. That experiment matters because it shows how carefully we need to use the word wormhole. A magnetic field behaving as though it crossed a hidden gap isn't the same as space-time opening a path between stars. Same word, very different claim. Then Miguel Alcubierre gave us another route. Instead of traveling through a tunnel, his theoretical idea changes the space around a spacecraft by contracting the region ahead and expanding the region behind. Again, fascinating physics. Again, not a working starship. So where does that leave the shocking claim from our opening? Right where science should leave any huge claim until enough evidence arrives, under investigation. A strange signal could become important. An odd image could force scientists to rethink an explanation. Something we can't identify today might become a major discovery tomorrow, but we don't know can't quietly become wormhole confirmed. That missing step is the whole story. Black holes give us a reason not to laugh at strange predictions simply because they sound impossible. Ideas connected with theory can later meet evidence in the real universe. Our source even uses that history to leave open the possibility that wormholes or white holes could someday move closer to confirmation. Someday isn't today. And maybe that's more exciting. Because somewhere in the universe, nature could still be hiding a structure that changes what distance means. Or humanity may eventually discover another path through space-time that nobody watching this has imagined yet. Until then, every strange signal gives us a choice. We can call the mystery solved, or we can keep asking the harder question. What evidence would finally make scientists say, without hesitation, that the doorway is real? What evidence would finally make scientists say, without hesitation, that the doorway is real? We don't have that answer yet. Wormholes remain one of physics' greatest open questions, waiting somewhere between mathematics and reality. If that boundary ever